Hi, in this video we'll be talking about modular arithmetic. So modular arithmetic is a part of mathematics but is heavily used in numeric computations in computer science. So while programming you would be needing the operations of modular arithmetic in your code. So we would be discussing the basic fundamentals, how it works, why it works, what are the various operations that are possible in modular arithmetic and their properties. So without any further ado, let's get into the topic. So in modular arithmetic, there is a notation that you need to understand first. That is, A is congruent to B mod C. Okay. Now, what is this notation that we have? So we would be understanding this using a diagram. Let's say you have C equal to 5, A equal to 7, B equal to 2. Okay. So what I'm saying is that you have this expression that is 7 is congruent to 2 mod 5. Okay. What is this actually saying? So this says that 7 is almost equal to 2 in the modulo domain of 5. Okay. So when you're taking 7 and 2 both in the modulo domain 5, they are both same. Now what does that mean? What is this modulo domain that we're talking about? So when you have modulo 5, let's illustrate this as a division of space into 5 parts. Okay, let's call 0 in one of the spaces, 1 in one of the spaces, 2 in one of the spaces, 3 in one of the spaces, and 4 in another. Okay, and then where does 5 goes? So to fit the numbers in this space, what we define as the 5 will go to the same class as 5 modulo 5. Okay, 5 will go to the same class as 5 modulo 5. So 5 goes to this class, 6 goes to this, 7 goes to this, 8 goes to this, 9 goes to this, then 10 goes to this, 11 goes to this, 12 goes to this, 13 goes to this, 14 goes to this, and then 15 goes to this, and so on, right? So this is how we are dividing the whole numbers in the space of modulo 5. So modulo 5 is doing a space partition in the whole numbers. Now, does this modulo work even for negative numbers? Yes. So as you can see, when you had 0, 1, 2, 3, 4, 5, 6, you went something like this in the spiral way, right? So if we go to negative numbers, how do you think it will work? So from 0, when you go to 1, you went on this side, right? So if you go to -1, you will reach this side. When you go to -2, you go to this side, -3, -4, and then -5, then -6, -7, and -8, -9, -10, so on, right? You can keep on going like this. So in the spiralish way, we can divide the whole integers into a space which has 5 regions, and any number in one space will be congruent to another number in the same space. So that is what this modulo operator actually means. Now for simplicity, you don't need to draw this diagram every time for this modulo C. You can simply think it about this way, that if there are two numbers, you want to check whether they are same or not modulo C, you can say that okay, you take A modulo C. So this notation A modulo C in programming means that you take remainder of A when divided by C, right? This is what we are talking about when we talk about remainders. Okay, so this is how you note down remainder in programming. So you find out A modulo C, you find out B modulo C. If they are both same, then you say that okay, they are congruent. Okay, so that's what this is meaning, that A mod C is equal to B mod C. So this notation over here that we talked about, this A congruent to B mod C is another way of saying that A when divided by C, whatever the remainder we get is same as B when divided by C, it renders the same remainder. So this is what this notation talks about. Okay, So A is congruent to B mod C. So A and B renders the same remainder when divided by C. That's what this is saying. Okay. Now let's look at some other definitions that this mean about. Like, it's just an alternative way of saying the same thing. Okay. So now let's say we have this notation, right? That means A and B are rendering the same remainder when you divide it by C. So this is also same as A mod C is equal to B mod C. So this is just another way of saying the same thing, that this A mod C is actually this, right? And is equal to B mod C, right? So if you write it this way as well, this means the same as this. So this is equal to this is equal to this, right? Okay. Only when you write things on only one side this mod, you use this congruent symbol rather than equal to, because they are not equal because you have not written mod over this side. But when you write mod in one side, then you use this congruent symbol. Okay. Another way to think about this would be that C divides A minus B. Now what is this? So if you take this expression from Euclid's theorem, we know that any number A can be written as some quotients times C plus R1, okay, and B can be written as some quotient times C plus R2, right? And now since they are congruent, they're both, the remainder are same. So this and this are same, right? So now if you find out A minus B, that is nothing but Q1 minus Q2 times C, and R1 and R2 are same because we have this property of modulo that the remainders will be same. So that part gets cancelled out. So this is the value of A minus B for some Q1 and Q2, whatever the values would be. And now we know that this is like two factors and C is dividing this number A minus B. So this is C divides A minus B. This representation over here, C bar A minus B, means that C divides A minus B. This is another notation just to say that divides. Okay. Also, if this is true, you can also say that C divides B minus A, right? Because same reasons, like it would be just Q2 minus Q1, but there would be just C. Okay. Another way would be, just another expression would be that A is equal to B plus K times C for some K. Now this should now become trivial because the remainders are same. So only things that differ are multiple of C, right? So if you add some constant times C, some integer constant K times C, you would be able to make them equal, right? So that's all the equivalent expression that you can talk about. Like this is one expression, this is another expression. Like if C divides A minus B, that is same as A mod B. So this is another expression. This is the, like this A mod C is equal to B mod C, and the original one, right? Original one is obviously there. So we would be using these notations interchangeably. Okay. And most common notation is this one. Okay. Now with these things in place, let's look at some properties that these follow, because these are the properties that we are going to use when we are computing numbers in programming. So let's quickly note down some properties. What happens if we want to find A plus B modulo C? So this is nothing but finding A plus B and then taking a remainder C. This is that number, right? This is a remainder when you divide A plus B modulo C, right? Now this can be written as A modulo C plus B modulo C whole modulo C. Okay, so this is like a first property. Okay, so we can write this A modulo C plus B modulo C whole modulo C. So you first of all find the remainder of A from C and B with C, and then add those remainders and then again take a modulo C. So what this claims is that these two numbers would come out to be the same number. Now why is that? This is pretty simple. Whenever you need to prove theorems related to modular arithmetic, you can just simply take q1 times c plus r1, because any number can be represented as in this form for any c, right? This is Euclid's theorem. Now you can take this one as this, and you can take the other one as q2 times c plus r2, right? And if you reduce this, this will be q1 plus q2 times c plus r1 plus r2, right? And now this part is divisible by c, so that will be removed anyways when you take remainder with c. So this is nothing but r1 plus r2 modulo c, right? Now in this part, this is direct remainder, right? Direct remainder with c. So this is r1, and this is nothing but r2, right? Direct remainder with c, and that modulo c. So as you can see, these two values are same, right? These two values would be same, like this and this are same, right? So that's why this theorem works. And sometimes these things help us in computing numbers. So that's why we are looking at these properties. So this is the first property. Let's quickly take a look at some other properties. Okay. So next property would be simply for subtraction, that if you need to find a minus b mod c, okay, this will be equal to same as a mod c minus b mod c whole mod c. Like there is no change in plus and minus, right? Okay. So this property holds for similar reasons, right? Now let's look at one theorem for multiplication. So for the multiplication as well, things are pretty similar. So if you want to multiply a and b and then take modulo c, it's same as taking modulo first with both the numbers and then multiplying it, and then again taking a modulo, because this multiplication can get bigger than c, right? So you need to take a modulo at the end, right? So this also holds, and you can check this using this, writing these expressions, and you will see that only r1 times r2 will remain on the left hand side, because everything else will be divisible by c, because there will be a c term and a c squared term. Okay. Another theorem that can help you at times is like you need to find a to the power b, okay, a to the power b mod c, and this is same as a mod c to the power b again taken mod c. Now why is this? So you can think in terms of binomial theorem. So let's take c1, c times q1, or rather we only have single q, so c times q times c plus r for this a whole to the power b, right? Now this can be expanded binomially. So if you open it with binomial expansion, you have b choose 0 times r, okay, to the power b, plus the rest of the terms will have this qc term, right? So if you take qc common out, then you have b choose 1 times 1 times r to the power b minus 1 plus b choose 2 qc plus so on, like multiplied by r to the power b minus 2 and so on, right? Like there will be a lot of terms. Now all of these terms will have this qc term in it, and this is divisible by c, right? So when you take a remainder, this gets removed, like this whole term gets removed and this is left. And as you can see, this is nothing but r is a mod c, right? A mod c, and that to the power b again taken a mod c, because this you need to take a remainder again. So these two would be same as well. So these are the three properties. If you quickly revise on that, so if you need to add two numbers, first take modulo and then again add. If you need to subtract, take modulo and then subtract. If you need to multiply, first take modulo and then multiply. If you need to take power, you can take the modulo inside base first and then get the power. Okay. So these are the sum properties. Now just to be sure that you are clear with the modular notation, let's quickly check what these values are. So what do you think is the value of 7 mod 3? So 7 mod 3 is nothing but what is the remainder when 7 is divided by 3? That's just 1, right? Because 6 is divisible by 3 and plus 1, so remainder is 1, right? So you can say 7 is congruent to 1 mod 3. So all these notations are same, like this is, right? So you need to find the smallest number in most cases, so that's what we are trying to find. Let's say you need to find 7 squared mod 3. So you can see that 7 square mod 3 is 49 mod 3, and 49 is not divisible by 3, and you need to go up to 48, and this will be 1 mod 3, right? Because 48 is divisible by 3 and 49 is 1 plus that. And in fact, if you rather find out the modulo first, so if you take modulo inside first, that is 7 mod 3 whole square mod 3, that is also equal to 1, so this part is 1, right? We already calculated that. 1 square mod 3, and 1 square mod 3 is same as 1, right? So 7 square is also congruent to 1 mod 3. Okay. Now let's quickly look at some negative numbers just to be sure that that's understood. What is minus 3 mod 2? Okay, so how do we find negative number modulo things? Okay, so in this case, what you need to do is that first remove this minus, okay, and find out. So this minus is nothing but minus 1, right? Minus 1 times 3, this is nothing but this, right? Minus 1 times 3 mod 2, right? So you need to find out the, sorry, mod 2, you need to find out the modulo of this number, right? Because let's keep the minus 1 for now. So this is same as minus 1 times 3 mod 2, and this is a positive number, so that's easy to find, that's 1, right? So this is minus 1 times 1, so this will be 1, minus 1 mod 2. So since we are doing everything modulo 2, this modulo 2 works everywhere, right? So now this is a negative number, but we generally try to keep things positive, right? The remainder of any number is always from 0 to r minus 1. So if you want to divide a modulo r, 0 to r minus 1, right? We try to keep numbers in this range. So this is not greater than 0, right? So now there is this property, right, that a and b are congruent if you add k times c to it. There was this nice property that even if you add some k times c, the numbers remain congruent, right? Like those two numbers are congruent. So what we do is that we add 2 to this. We add 2 to this because adding 2 doesn't change anything, right? 2 is already divisible by 2. So adding 2 won't change a thing. So if we add 2, so this is minus 1 plus 2 mod 2. So we can always add and subtract this modulo thing from this number because that's not going to change the remainder. And this will become 1 mod 2. So minus 3 is actually 1 mod 2. And in fact, this you can use for any negative number. For any negative number, if you need to find the modulo, like minus 4 mod 7. So first of all, make this 4 modulo 7, find out this minus 4 modulo 7, and that doesn't change, right? 4 is already less than 7, so that will remain 4. And then once you have this, add 7 to this. So 7 minus 4 mod 7, and that is equal to 3 mod 7. So minus 4 mod 7 is actually congruent to 3 mod 7, right? Minus 4 is congruent to 3 mod 7. Okay, so this will hold. So why did we do all these like arbitrary kind of notations and all? Why did we introduce all of these things? Okay. So these modulo arithmetic would help us calculate numbers when we need to calculate the answer modulo some number. Okay, so in a lot of cases you will be given numbers to be found when the things change, and you would be asked to find the answer modulo some c. So a general example of that could be like you'd be given a problem that you need to find, say, a multiplied by b. Okay, and let's say a is up to 10 to the power 9, okay, and b is up to 10 to the power 9, and you'd be asked to find out this number modulo 10 to the power 9 plus 7. Okay, so these are the these are the usual C values that are used in problems. So this is actually a prime number. 10 to the power 9 plus 7 is a prime number. So that's why these are sometimes preferred in problems. Now, when you would need to calculate something like this, what happens is that you will, if you did not had this in the problem, if you try to save a in an integer and b in an integer, okay, if you save both of them in an integer and then multiply those two values, okay, what happens is that the answer could be of order 10 to the power 18, right? And that can easily overflow integer. So we will have this overflow problems in computation of numbers. So for those problems, the problem statement generally has a modulo by which you need to find the answer with. So in that case, you take all the operations that you are doing in an algorithm modulo some prime or some number that is given in the problem. So with that, you will have to do the operations. So whenever you are doing some operations in the problem, you will need to be sure that that property holds, right? You will need to distribute mod into two of them. So again, in this problem, let's suppose you had to do this. So you can easily keep things less than equal to this number and save numbers in a long integer, okay? So in long, the range is up to 10 to the power 18, right? In fact, it's up to 10 to the power 19, but still, it can support up to 10 to the power 18. So if you save both the numbers in long, you can multiply them, okay? So with these modulo operators, now even if the answer is actually overflowing, like even if you need to find out the answer that is really large and you cannot store it in a variable, you will be able to report that modulo some given value in the problem. So that is why modulo is used in problems, and you will be needing these properties that we discussed, like this first property that if you had to add, you can first take mod. So individually both of them can be bigger than C, and as a result this is getting quite large. So first take mod and make both of them less than C and then add so that it doesn't overflow. Similarly in this multiplication, individually both of them, if you multiply them, it might get bigger than the limit of integer or long, but if you take mod first and then multiply, it might remain in the integer, in the domain of long. So simply 2 to the power, suppose you need to find 2 to the power 100, right? So in that case, or rather let's think about this. If you need to find 10 to the power 18 square, 10 to the power 18 square, okay, so that's not possible because it will be 10 to the power 36, and storing that in a long is not possible. So if you take modulo first with some smaller prime that is given to in problem, generally it's 10 to the power 9 plus 7. So if you take it smaller prime, you take a modulo with that, so this number becomes smaller, right? It is now less than 10 to the power 9. So now you can square it and it will be up to 10 to the power 18. So this is how modulo is going to help in computation in programming. So that's all. See you in the next video.